mini workshop on dynamical systems of Transseries, which is part of the semester of Transseries, tail geometry in general. Many thanks to all the speakers in the workshops. For example, yesterday, Sunday, the Institute was proud of people preparing their talks. So many thanks to them. I see a few of them here. Okay, so let's begin. Our first speaker today is Marco Abate from Pisa University, and he's going to explain us a few things about multipoint Julia theorem.
Okay, thank you. Please, first of all, let me know if the mic works.
Yeah, it's fine. We can hear you.
Work?
Yeah. It works. Okay, good. So thank you. Good morning, everybody. I'm very glad to be here, and I really want to thank the organizer of a meeting, of a mini workshop, on the whole thematic period, and all the organizers for inviting me here. In particular, because my talk has unfortunately nothing to do with Transseries and only very slightly something to do with dynamical systems. But I promise there will be at least one infinite series at one point. At least one, I put it there exactly for this content. Now, actually, I hope that it might be interesting anyway, because the aim of the talk is to show some techniques to get particularly, let's say, deeper properties of holomorphic self-maps of a unit disk, taking into account the higher derivatives. Usually we will see a number of examples. Usually when one starts studying properties, it's clear that the first derivative is important, for instance, for dynamical reasons, but also for other kind of problems. And it becomes more difficult to understand the effect of a higher order derivatives. And what I'd like to show you today is a systematic way for finding out how the effect of the higher order derivatives on the behavior of a function. I will give you a couple of examples. So let's start very classically with a classical SCHWARZ-PICK lemma, which I think everybody knows it here. But anyway, it says that you have a holomorphic self-map of unit disk. Then necessarily you have two things which are contracted, or more precisely not expanded, which are this quotient over here and this let's say differential quotient. And if you have equality at one couple of distinct points in the first line or in one point of a second line, this can happen if and only if the map F is actually an automorphism of a disk. There is a geometric way of stating this, and it can be done introducing the POINCARE distance, which is defined in this way, which is the invariant under the action automorphism of a disk, and it actually comes from an Hermitian metric, and it is up to constants the only Hermitian metric on the disk invariant under the automorphism and with constant Gaussian curvature, negative Gaussian curvature. And so the first line of the SCHWARZ-PICK lemma can be expressed in this way, saying that all the holomorphic self-map of the unit disk are one Lipschitz weak contraction of the POINCARE distance. And as you can imagine, as you all of you probably know, this gives you an equicontinuity property, which implies compactness property. You can do a lot of things, in particular, starting from here and from another thing that I'm going to mention before. This is the starting point of dynamics on the unit disk. Okay. The second line of the SCHWARZ-PICK lemma can be expressed saying that the function of the self-map F is a weak contraction for the Poincare metric that Mr. McKenna was saying before, but we are interested in expressing in a different way. Introducing, this is very classical, the so-called hyperbolic derivative of F, which is just the quotient of two two sides, the left-hand side, the right-hand side of the inequality in the SCHWARZ-PICK lemma. You just take this quotient. And so the second formula in the SCHWARZ-PICK lemma say that the absolute value of this map is always at most 1. And it is 1 at one point, if and only if it is always 1, and then if and only if F is an automorphism. Okay, this is very classical. But there is one thing which doesn't, well, a caution that this hyperbolic derivative is not holomorphic. The usual derivative is holomorphic. The hyperbolic derivative, it is not. There are some absolute values there. And well, this was apparently the situation until 2004, when BEARDON and MINDA had the apparently very simple idea, but actually powerful, to do the same with the first inequality in the SCHWARZ-PICK lemma. And they introduced what has been called in several different ways, but let's call it the hyperbolic difference quotient, which is defined as the quotient of two sides of a first inequality in the SCHWARZ-PICK lemma if z is different from w, and it is the hyperbolic derivative if z equal to w. So it is a function of two variables. And again, the SCHWARZ-PICK lemma says that the absolute value of this hyperbolic difference quotient is always bounded by 1, and you have equality at a pair of points if and only if F is it is an automorphism. Okay. What is the gain? The gain is that now if you fix the second variable W naught, what you get is this, the map sending Z to F star Z W naught is holomorphic. The only question will be Z equal W0, but it turns out it is a removable singularity, so it is holomorphic also there. And moreover, if F is not an automorphism, then this map over here is a holomorphic self-map of the unit disk, exactly as a F at the very beginning. Which means, and that was the idea of BEARDON-MINDA, that you can write down a SCHWARZ-PICK lemma for this map F star, W0. And you get what they call a 3-point Schwarz lemma. You take an F which is not an automorphism, and then you have this contraction omega F star Z D, omega F star of WD is bounded by omega ZW for all Z, W, and D. With equality for some V naught and 2 different points Z and W, if and only if, well, F cannot be anymore an automorphism because to be excluded, but the equality turns out to be a characterization Blaschke product of degree 2. So let me recall very fast what is a Blaschke product. This is an automorphism. All the automorphisms of D are this form, a rotation times this Mobius map. And a Blaschke product of degree D is just a rotation times the Möbius maps with center of V1, DD can be different or the same, but just point to the unit disk. Okay, so a Blaschke product degree 2 is just a product of two of these, and then possibly a rotation. Very fast, how one can prove this? Well, the inequality-free just SCHWARZ-PICK lemma applied F star to F star. There's nothing to say. If the equality holds for some V naught, then by the usual SCHWARZ-PICK lemma, F star of V naught should be an automorphism. Okay. So if we multiply, you remember F star of was a quotient where at the denominator there was a Möbius map. So if you multiply this by the Möbius map, you get an automorphism times the Möbius map. This is a Blaschke product of degree 2. And then you can recover F just composing by the inverse of an automorphism. And pre-composing, post-composing Blaschke product with automorphism, you still get Blaschke product of the same degree. And so we get that F is a Blaschke product degree 2. Well, conversely, if you start with a Blaschke product of a degree 2, you just do a computation, you end up with an automorphism. And well, after that, BEARDON-MINDA started playing with this idea, and they got a 4-point Schwarz lemma, which is stated like this. And again, there is also the equality case. Well, we get the equality case if and only if it is Blaschke product degree 2, and the 4 points involved, U, V, W, and Z, are in a specific order along the geodesic in the disk. I'm not going to prove the equality, but I will show you why something like that should happen. And well, RC here is the non-Euclidean rotational angle pi. If you center at the point C, if C is 0, just sending Z to minus Z. If C is different from 0, it's the same up to an automorphism of a disk. Okay. So in particular, it is an involution. Okay, the sketch of a proof. Well, you start with a triangle inequality. Then you apply to here, to this piece over here, the SCHWARZ-PICK lemma. Versus point SCHWARZ-PICK lemma, we get this. Now we exchange W and V in the first term. Well, actually, F star of VW is not the conjugate of F star of WV or something like that. But the point is that they have the same absolute value. And so since the Poincare distance from the origin depends only on the absolute value, we can do this without changing anything. And then we just put, we replace this term over here with the same inequality that we got here. So instead, we applied it to VW instead of ZV, and we get the assertion. To get the equality, we should have equality at all steps. So in particular, it should be a Blaschke product degree 2, because we need to have an equality from the first line to the second line. And if you check the other equalities, they can happen only if these 4 points are on a geodesic in the correct order. Okay, this seems to be a game, but actually it turns out that with these two formulas that I showed you, you can obtain a lot of other formulas which were already present in the literature from the 30s up to the 2000s. All of them were proved in different ways, ad hoc computations and complicated ways sometimes. And they are all just consequences of these two statements. One example, let's take V equals Z and W equals 0 in the 3-point SCHWARZ-PICK lemma. We get this formula that when F0 equal to 0 gives a well-known inequality due to Dieudonné, saying how far is F prime from the quotient F over Z. Okay, this is just that formula rewritten in Euclidean terms. We take the 4 points, we take U equal to V equal to W, we get this statement over here, which is equivalent, you unravel the definition, to this formula, that when F0 equal to 0 becomes this, again, well-known sharpening of the Schwarz lemma. If F is an automorphism, F prime of 0 is 1, so this is just the standard Schwarz lemma. But if F is not an automorphism, F prime of 0 is strictly less than 1. And so that quotient over there is strictly less than 1. So we get something slightly better than the usual Schwarz lemma. We would just say F, absolute value of F is bounded by the absolute value of Z. But again, this was already well known, but now we can get it immediately in this way. Another example, you take U equal W, V equals Z, and we get this statement over here. So this is a sort of SCHWARZ-PICK lemma for the absolute value of a hyperbolic derivative with a factor 2 in front. If you unravel this definition, we get this Gaussian estimate, which again was well known, but proved in a completely different way. And just to give you an idea why this estimate can be useful, let me show you how to use it to prove an actual theorem. This is a well-known theorem by BURNS-KRANTZ. The problem they discussed was the following. We know another way of presenting the SCHWARZ-PICK lemma is saying that if you have a holomorphism map of a disk with a fixed point where the derivatives at that fixed point is the identity, then it is the identity. Okay, so if you have something which is of a form f of z is equal to z plus or something of order 2, it is actually just z. And I wanted to know what will happen if a fixed point were not inside but in the boundary. This is a typical situation linked to the dynamics when you have a holomorphic map of a unit disk which has no fixed point inside. Then there is only one point in the boundary, the Wolff point, where the sequence of iterates is converging there. And furthermore, the map has a non-tangential limit at that point, That point is a fixed point from a point of view of non-tangential limit. And moreover, you also have a non-tangential limit of a derivative, and this is bounded by 1. Okay, so it works like the fixed point inside for the SCHWARZ-PICK lemma. But of course, so you can write that a map, let's say that this fixed point, the Wolff point is 1 for simplicity. You can write that a map as a fixed point start like f of z is equal to z plus something nearby the fixed point. But of course, you cannot say it is the identity because we have many of them. It turns out, as has been proved by BURNS-KRANTZ, that the exact statement is that you get the identity if you do not have anything else the second and the third degree. So if f of z is of a form z plus little o or sigma minus z to the cube, then it must be the identity. And there are many different proofs of this, but the proof I would like to show you comes from this recent result by Bracci, Krauss, and Roth, which is actually a particular case of a much more general result we got, and they also had some several variables generalization, which is somehow more invariant, in the sense that it is expressed in terms of hyperbolic derivatives, which has the advantage of behaving well when you compose with an automorphism. And you're taking any sequence going to the boundary. So you can change by an automorphism, the sequence can be tangential, non-tangential, it doesn't matter. The point is that if the absolute value of the hyperbolic derivatives goes to 1 up to a term of slightly faster than 1 minus e to the n square, then f is an automorphism. And then the absolute value is equal to 1. And actually, it is possible to prove this statement just using the Gaussian estimate method showed before, because from one side, well, you take a logarithm of this formula 6, and what we are saying is that the lim sup of that quotient is 0. That's what it means, that formula. But on the other hand, if f is not an automorphism, we can apply the Gaussian estimate, which was the absolute value of h is bounded by the things in between, in the middle of the square brackets. Then you put a log in front, you add the subtract 1, and you take the expansion, the usual expansion, and we get something like this. Then we can divide by 1 minus e square, and we go to the boundary. This lim sup now is bounded by that quotient over there. And now this quotient is strictly less than 0 because f is not an automorphism. And so we know that the absolute value of a hyperbolic derivative is strictly less than 1. But we had as hypothesis that this lim sup should be 0. So this is a contradiction. And the contradiction comes from the fact that we are assuming that f is not an automorphism. So it should be an automorphism. And by the way, the statement is sharp. If you take this function over here, then it has exactly terms of degree 2, and then higher order terms, and clearly it is not an automorphism. So this is a sharp statement. Okay, from this we can get to the BURNS-KRANTZ theorem easily. Just because, well, using the Cauchy formula to represent the derivatives of f in terms of f, it's easier, not difficult to see that the formula 7 implies the condition in the BRACCI-KRAUS-ROTH theorem. So we get that f should be an automorphism, and the only automorphism which start like the identity is the identity. Okay, so this is another way of proving the BURNS-KRANTZ theorem. Well, okay, why stop here? Okay, we did it once. But now, if f, we just remark that f is not an automorphism, then f star is an automorphism map of D. And so we can repeat the process. We can compute the hyperbolic difference quotient of a hyperbolic difference quotient. And this has been studied by a few people, and actually, as we'll see faster, because then I will go to a different application of these techniques, it's a way to involve in the estimates the higher order derivatives. So let's define some notation. Let's call what we call f as f star, we'll call it now delta z1 or f of z. And in this way, it's easy to write down what it means to be delta of zk up to z1 or f of z, just the hyperbolic difference quotient of the map defined with k minus 1 terms. Okay, just like iterate hyperbolic difference quotient. And well, it turns out that they are all bounded by 1 with equality in 1 point, if and only if it is a Blaschke product degree K. And if it is not a Blaschke product degree most K, then it is a holomorphic self-map of a unit disk, and then you have the Schwarz-PICK lemma for this iterated hyperbolic quotient with equality if and only if it is a Blaschke product degree K plus 1. Okay, this is just the same thing we did, just applied by using induction. One possible application of this turns out that in the literature there was this definition of Pascal invariant derivative, which is essentially instead of taking the expansion at the origin, you want to take an expansion at a different point in the disk, and you just conjugate by an automorphism, so you move it this z naught at the origin essentially, and then you take the usual series expansion, and the number you put in here, oops, sorry, these are called the partial invariant derivatives. And well, d1 is just the hyperbolic derivative, and there are formulas. D2, for instance, can be written in this way, involving, you see, the second derivative, and then some strange combination of first derivative, f, hyperbolic derivatives. The formula are not really, I mean, to me, they're not very important. Yes?
So the first equality, so the series is converted.
Yes, this is a definition. This, I mean, we are just taking the term at the left. We are just, it is an homomorphism of map of a unit disk, and we are just taking the expansion at the origin, the usual power series expansion at the origin. And we are just giving a name to the coefficient of this power series expansion. And actually, it is possible to compute the hyperbolic, the iterated hyperbolic difference quotient at the same point z naught using these derivatives, these invariant derivatives. And for instance, well, you have a couple of formulas here, the 2 ones and the 3 ones. Why these are useful? Because we know that the iterated difference quotient here are bounded by 1, and so this immediately gives you bound by 1 also the terms on the right hand side automatically. And indeed, for instance, we had this formula by Yamashita, was known before, but there is this bound again with equality if and only if f is a Blaschke product. And if you do it for the third one, you get an estimate involving the third derivative, and again we'll get equality if and only if it's a Blaschke product degree 3, and so on. And now you can play, for instance, instead of having all the points equal, you can put some zeros over there. And this yields a higher order version of the Dieudonné estimate. For instance, this one, which is very complicated, but well, this is taking 0, z naught, and 0, yields this formula. And you can recognize here there is something like the Dieudonné estimate. But possibly slightly better is this one, which, well, there is a general statement over there, but if you have f0 equal to 0, f prime equal to 0, you get this estimate of a derivative with a 2 over here, and this is a higher order expression of Dieudonné. I mean, this is just to give you an idea how playing with this kind of things, you can get estimates involving higher order derivatives in a systematic way. Okay, when I read this paper by Beardon and Minda and other papers like this, the first thing I thought, well, let's try to do the same with the Julia-lemma. And indeed, in the original Beardon-Minda paper, there was a statement that they call it the three-point Julia-lemma. But let me recall what the Julia-lemma is. It is a Schwarz-PICK lemma at the boundary. So you take an homomorphism map of unit disk, you take a point in the boundary, and you define this number here, which is the boundary dilation at sigma, which is just a length of that quotient. Okay. Assume it might be plus infinity, but assume that it is finite. Then it turns out that f admits a non-tangential limit, f of sigma, which is still a point in the boundary at sigma. And furthermore, we have a sort of Schwarz-PICK lemma. I will explain you in a second in which sense it is a sort. In the sense that we have now this quotient, which is not necessarily contracted, but it is contracted up to multiplication by this number over here. And again, we have equality at one point and thence everywhere, if and only if f is an automorphism T. Geometrically, the Schwarz-PICK lemma said that if you have a fixed point inside, oh, well, not even if you don't have a fixed point inside, the Schwarz-PICK lemma says that you are sending Poincare disk, that is a disk for a Poincare distance, into Poincare disk of the same radius. Here, if we define the this statement over here says that we are sending now whole cycle into themselves. The whole cycles, they have an invariant definition in terms of a Poincare distance, which is actually one way of proving the Julia-lemma. But geometrically, they are Euclidean disk tangent to the boundary at the point sigma in this case. And so this is saying that if you are, I think I wrote it here, that's the analytical definition. And this is an Euclidean disk internally tangent to sigma. And so this statement, the Julia-lemma, it says that if beta is less than is finite, then the image of this circle centered at sigma is sent into the circle center f sigma with a radius multiplied by beta. And actually, this is together with his brother, which is a Wolff lemma, which is the main point, the main technical tool for studying a dynamical system of a holomorphism map of the unit disk. When you have a fixed point, you just apply Schwarz lemma, and then it's clear. If you do not have a fixed point, these are the tools that allow you to prove a Wolff-Schwarz theorem, saying that everything is convergent to the boundary. Anyway, Beardon and Minda had what they call a three-point Julia-lemma, which is this one. That, well, they have taken 3 points, ZW and V, but Z and W are not arbitrary. They have that condition over there. And that what they are saying is that they got a slightly better inequality because this mu f v z w, this formula over here, is strictly less than 1. So it's slightly better inequality. So from this point of view, it improves the Julia-lemma and actually recover when w is equal to v a result due to Mercer, which were already in the literature. On the other hand, at least in my opinion, the hypothesis is somewhat unnatural. I don't see why I should choose Z and W. I mean, I could take W in a different way. And moreover, V appears only here. And when, of course, the natural thing to do will be to take the infimum of that number with respect to V. give it a name and put that into the equation. So the third point is not really there. It's just an artifact of a proof. And I don't know any application of this, by the way. So I decided to do something different, which was something more natural from my point of view. And first of all, let me recall you very quickly a couple of things around this. I define the dilation beta as the lim-inf of a quotient. Actually, there is a different definition. You can define this beta of sigma tau, 2 points of the boundary, as the suprema of that quotient. Those are the left-hand side, the right-hand side of the formula in the Julia's lemma. There. You F sigma, you call it tau, and you take the quotient between the two. Julia's lemma say that it is bounded by beta. So we forget this, and we just take this quotient, and we take the supremum. And it turns out that the beta, defined as the lim-inf of the quotient, is actually the infimum of this supremum when tau ranges over the whole boundary of the disk. And more precisely, if it is finite, there is only one tau where this supremum is finite. In all other cases, it's infinite. And the tau is exactly the f of sigma in the Julia's lemma. So this is a different way of describing the Julia's lemma. And furthermore, as soon as one has this characterization, it's easy to get this estimate from below of this dilation. And this just follows from this the triangular inequality, the usual Schwarz lemma. If you unravel the final inequality, you get exactly the thing over there. And we'll come back to this inequality several times. Connected to this, it's the famous Julia-Wolff-Carathéodory theorem that says that not only f, when beta is finite, not only f has a non-tangential limit, but also the incremental quotient and the derivative have a non-tangential limit. And this non-tangential limit is essentially given by beta, which is in some sense the derivative, the angular derivative of a map. In general, it is angular derivative when it is multiplied. F prime of sigma is the angular derivative. So you have F sigma is sigma bar. But for instance, in the Wolff case, when F of sigma is equal to sigma, F of sigma times sigma bar is 1. And so beta is exactly the angular derivative. And in particular, so this limit in that particular case is a real number, which is something which is useful in several applications. Okay, so if what I would like to do, we take the hyperbolic difference quotient, which is again a self-map of a unit disk, and I want to see if we can write down the Julia lemma for the hyperbolic difference quotient. To do that, I need to check whether the boundary dilation, this beta for the hyperbolic difference quotient, is still finite. And luckily it is. There is actually a very nice formula for computing the dilation, the beta for f star, starting from a dilation of the original f. And that is the formula over there. And we can also compute now the non-tangential limit at sigma of f star. This is a nice formula. And one important thing is that by the definition, the characterization I gave of beta as the inf of a sup, we know that beta f is always greater than that quotient. with equality if and only if F is an automorphism. And so, in particular, beta F star, which is given over there, is strictly positive as soon as F is not an automorphism. So we are exactly in the good condition. Well, yes. We are in a good condition to write down a 3-point Julia's lemma, but before that, let me just remark one thing, that already here we got something new. Almost new. I noticed before that beta is bounded below by 1 minus f of 0 over 1 plus f of 0. Let's write it down for beta star. Okay. It turns out, well, we unraveled the definition. It means this. In particular, we got this statement over here, which you just put everything on the other side, and we get this estimate that when F is not an automorphism, is actually better than the previous estimate, because 2 over 1 plus absolute value is strictly larger than 1 when F is not an automorphism. So, I mean, just here we get an improvement to the standard estimate, but we'll get something much better. So this is the 2-point Julia's lemma. It is just the Julia's lemma stated for F star, because now we know that the beta star of F, that is beta of F star, is finite. And again, equality at one point if and only if F is a BRACCI product of degree 2. And then you can then apply the Julia-Wolff-CarathÉodory theorem to F star, and you get these two statements, just for completeness. Well, this theorem was actually already more or less in the literature, in the sense there was this result by Mercer that, okay, I'm not going to read it. The statement is very complicated, but this is the Euclidean statement of that one before. This is saying that I mean, as I told you, the Julia's lemma says there are some disks which are sent into disk. If you write it down in a Euclidean way, in computing what is the center of a disk, the radius of this Euclidean disk, you get something like this. But sure. Yep, of 2-point Julia's lemma that is. But I mean, at least from my point of view, when I wrote my version, I understood what I was doing. Here, well, it's a formula. I mean, the point is that the Euclidean geometry is not the right one to study the geometry of a unit disk. You need to use the hyperbolic geometry. Corollary, we get this kind, for instance, this sort of Julia's lemma for the derivative of f at 0. And well, just assuming that f of 0 equal to 0, then f star becomes fz over z, and beta f star is just beta f minus 1. So you write down the previous statement, and we get this one, which is, as you can imagine, particularly interesting when f of sigma is equal to sigma bar. F of sigma is equal to sigma, so you get 1 over there. Okay, and this was an observation that if you have a fixed point inside, for instance, the origin, then the derivative must be greater than 1. So the previous corollary says that when f of 0 is equal to 0, f of sigma is equal to sigma, we got this estimate. And you can write it down in a different way. And this is what has been done by Cowen and Pommerenke in 1982, which says that actually, if you have a fixed point inside and you have many fixed points in the boundary, then the sum of all these numbers, 1 over f prime minus 1, But we saw before it was bounded by that writer. You see, there, if you take 1 of f prime minus 1, it is bounded by 1 minus f prime of 0 to the square over the other thing. And actually, this is true even if you have many points. All of them together, you sum all of them together, all these numbers, they are bounded by the same number. Pure equality if and only if f is a Blaschke product degree n plus 1. And the proof, it's essentially an application of the previous corollary. We can assume 0 equal to 0, and we would like to prove that this inequality by induction on n. Okay, and then one set z equal to 0, and we get the statement. Well, for n is equal to 1, it's just what we did before, it's the previous corollary. If it also n minus 1, then we can find an auxiliary function h so that that difference over where there can be written as 1 plus h over 1 minus h. Then you define g as z times h. You apply the previous corollary to g, and it turns out that you get the statement you can add one more term to this sum. Okay, yes, 5 minutes. This is just to show how the 2 points Julia's lemma can be used to get something which was already in the literature, but now we get something new. We iterate the construction as before, the iterated hyperbolic quotient. And of course, you can write down the multipoint Julia lemma, multipoint Julia theorem, with equality if and only if it is a Blaschke product degree k plus 1. And we can do a couple of applications. First of all, we already saw a couple of estimates on the boundary dilation coefficient. But now, since we can compute recursively the boundary coefficient, dilation coefficient of the iterated hyperbolic quotient in terms of the original boundary coefficient, we have an estimate on we have actually a whole family of estimates that was improved for the first time by Fournier and Roth in 2019 and in a completely independent way. I didn't know their paper while I was writing mine, and conversely. We find that only later on. We had this kind of estimates involving all the iterated hyperbolic quotient on an arbitrary sequence of points in the disk, with equality for one sequence and then for all, if and only if it is a Blaschke product degree k plus 1. So it's also a characterization, a new characterization of Blaschke product, if you want. And the case k equal 1 was also proved independently in 2021 by Kudryavtseva and Solodov. And if you want it a slightly more understandable statement, you take all the points equal to 0, and we get this estimate that it looks like the statement over the original estimate. The only point is that we introduce another inequality in the proof. So the equality is not only when the Blaschke product, but we need also another condition for the equality. Oh, just to give you an idea, for instance, for k equal 2, those estimate becomes this thing over here, which is better than the previous one. In particular, you see then the second derivative comes into play. If you take k equal to 3, the third derivative will come into play. Okay, a conjecture. Now let's take a Blaschke product, the infinite degree So it's an infinite product, converging infinite product. The conjecture is that now we should have inequality here for every sequence, an infinite sequence of point on D. And we suspect we also should have this statement, again, for BRACCI product infinite degree. This was the other one. And, well, I'm pretty confident that this should be true, even though it is not completely clear to me how to prove it. But what I really do not know is what happens for self-maps which are not BRACCI product, not even infinite BRACCI product. We clearly have the inequality, just because we have inequality for all finite terms, so we have the inequality at the end, which in particular means that that infinite series over there is always convergent. But I don't know if it is a strict inequality or not. For instance, if it is an inner function, whether we have a strict inequality or if you have inequality anyway, that I don't know. It's just a conjecture with an infinite series in it. Okay, let me finish in the last 2 minutes, give another application. We saw the Cowen-Pommerenke estimates when we have a fixed point inside and a number of fixed points in the boundary. The question is, can we get better estimates using this kind of approach when the point inside is not only a fixed point, but also a critical point? So when f prime of a fixed point is 0. Well, let's assume that the point is 0 and it's a critical point, so f prime of 0 equal to 0. Then using the previous formulas, we get, if you remember before, we got something like f sigma or sigma minus f prime of 0 over 1 minus f prime of 0 square less than beta minus 1. Now, f prime of 0 is 0, so that doesn't say anything, but we go to the second derivative, we get this kind of estimate with f prime, f double prime of 0 over 2 and beta minus 2. In particular, if f of sigma is equal to sigma square, we got this estimate over here. And so the natural thing is, okay, what happens if we have many points in the boundary where f of sigma is equal to sigma square? And we get what you expect. Oh, well, first I stated what happens when we have a critical point of higher order. So all the first k minus 1 derivatives are 0. And then you get what you expect. In the sense that you get sigma k instead of sigma square and 1 over k factorial f, k derivative of f instead of a second derivative over 2. And we have a beta minus k instead of a beta minus 2, is as expected. And the proof is just that you can do it computing using the delta of origin k time. You just compute that, it turns out to be what you expect, f over z to the k is z different from 0, and 1 over k factorial f over k derivative of k is equal to 0. So you just apply the previous statement to this function over here, delta okf. So this is easy. And if the critical point is the origin, and we have m points in the boundary which are such that f of sigma j is equal to sigma j to the k, then we get the generalization of the Cowen-Pommerenke estimate as we expected. That is, instead of having minus 1 on the left hand side, we have minus k. And instead of having f prime of 0, we have the kth derivative at 0 divided by k factorial. Pure equality if and only if it is a BRACCI product of degree n plus k. This is completely expected. I just the standard Cowen-Pommerenke estimate applied to this function over here. And then I said, okay, but here we are mixing two things. We are saying that 0 is a fixed point, and then we are saying that it is a critical point of order k. What happens if you take another fixed point, which is a critical point of order k? Well, it should be easy. You should just conjugate by an automorphism, you should get that. But actually, when I started writing down the conjugation, it turns out that it was more complicated than expected. From 2 points of view. First of all, to understand what was the condition we have to put in the boundary. And then after a few computations, it turns out that it is sort of natural in the sense that we have to Z0 is a fixed point, which is a critical. Sigma j's are the point in the boundary, and we have a sort of a conjugate with an automorphism of a disk, bringing Z0 to the origin and putting a k power. So instead of having, in the first case, it was f of sigma equals sigma to the k. In this case, f of sigma should be this thing over here. And up to here, it was well, something I expected. But the final statement is that there are other terms in the inequality. There is not only the derivative, but you have to put this weight over here, measuring the distance from the origin, if you want, of a distance from a boundary, with the right weight, k minus 1. And there is also this term over here that I mean, it is false without it. So you have to put it. And the only way, the only way I found to prove this was to apply the multipoint Julia lemma, the general statement of the multipoint Julia lemma that I showed you before, and use that in the proof, and not just applying the usual Julia lemma to a particular function. Well, maybe even just because I don't know how to do it, but anyway, this is the result we get. This is just again. The point of this talk is to show you that using this procedure, we have some sort of standard technique to study what happens, phenomena that depends on higher order derivatives. You just take the higher order hyperbolic differential quotient, and they automatically involve higher order derivatives. Thank you. That's all.
Thank you.